So next we have cutoff points. We have to draw the line somewhere. So how low does a person have to be before we say this is a statistically significant result? How confident does the researcher want to be in his or her conclusions? Or in other words, where does the researcher draw the line? And where the researcher typically draws the line in social science studies is at 5% odds. We only want a 5% chance of being wrong. This is usual in the social sciences. That's a norm. In the medical sciences, often we want 1% odds. We only want a 1% chance that this medicine isn't going to be effective if we give it to someone. So if you own the casino, what do you want the odds of a customer winning to be set to? What kind of odds are you going to be comfortable with? It's usually really low that you're going to actually win a game if you're in a casino. But just as the casino owner decides what odds are okay for a customer to win, so does a researcher decide what odds are okay for rejecting the null hypothesis and moving the treatment or medicine to the next stage of testing. We call this alpha, and it is just the level of confidence set by the researcher. So alpha is the probability that the researcher will accept in order to reject the null hypothesis. So you'll remember rejecting, this funny phrase, rejecting the null hypothesis. We joked and said that researchers like rejection, they're weirdos, right? But remember, rejecting the null hypothesis is like rejecting the conclusion that the guy is innocent. The guy is in fact guilty. We have evidence. Rejecting the null hypothesis is saying, oh, we started out saying this medicine didn't make a difference, but look, we have enough evidence that it does. And we only have a 5% chance that we're wrong or a 1% chance that we're wrong. So we call it alpha. It's a Greek symbol. We just write it as an A, but it is actually a Greek symbol. And we just set it that this is the decision the researcher makes. How comfortable does the researcher want to be? In our work in this class, we're always going to assume it's 0.05, or there's a 5% chance, or 0.011%, meaning that the researcher won't reject the null hypothesis unless there's a chance of less than a 5% probability in the case of alpha equals 0.05, or a 1% probability if alpha is set to 0.01 of obtaining these scores by chance. So this is what we're looking for. Now, one thing to notice is this right here. You never have to calculate this. It's always written down for you. So you're going to look for it. What are the probabilities that the researcher is looking for? And as you're looking for it, I'll show you how you'll often see it. You might see it written as alpha, or in your book, very often they say something like this. So alpha corresponds to the statistical conclusion that we would write p less than 0.05 or p less than 0.01. So what this means is this. If we interpret this statement right here, it means the probability, that's what the p means, of obtaining scores like this by chance, of obtaining, say, eczema symptoms that are this low, just by chance, are less than 5%. And if that's the case, then we reject the null hypothesis and find that this evidence supports the research hypothesis. Your book might say something like this. The significance level was set to, the significance level was set to, and then they'll tell you what it is, 0.05 or 0.01. So to understand where we draw the line or set alpha in a one-tailed test, we're going to look at this image and do a few different iterations of it by erasing what we just do and drawing it differently. So first off, you know that in a one-tailed test, we're just looking to determine whether a score, a treatment score, falls in either the lower end of the distribution in a low-tailed test, or at the upper end of the distribution in a upper-tailed test. And this line is our line for alpha, which relates to the probability rejecting HO, and it will always be stated in the problem for you. You never have to try and figure out what alpha is. So first off, let's say alpha is set to 0.05. The researcher just wants a 5% probability of making a mistake. So that means that the researcher is going to look for a score that is different from 5% of the value. So in a one-tailed high test, let's start there. So we have now a directional test. We have one-tailed high. This means that the alpha is going to be set at the point where 95% of the scores are lower than the score that we're interested in. So we can see here that if we drew the line right here, that would be like alpha at 0.02. 98% of the scores would be lower. We're looking for 95% of the scores. We know that if alpha was set right here, well, we would have 50% here and 34% here. 34, excuse me. And so we know that this would be 84% of the 84th percentile, so to speak. And so we need a number between the 84th and the 98th. We're looking for the 95% marker. And it's going to be somewhere right about here. And this is where 5% of the scores will be up here. And 95% will be in here. And so if alpha was sent to 0.05 in a one-tailed high test, the cutoff point would be whatever z-score corresponds with this point right here, whatever that z-score is, that what we call the fail region that makes the researcher unhappy will fall within this broad general area in the center. So all of this, any score that we get that falls in this region would cause the researcher to say, nope, there's no difference between this medicine and the control condition. The medicine didn't work. So this would be the fail region. And what it actually means is that we fail to reject the null hypothesis. However, if the score that the researcher gets from the sample falls within this tail region, this little region way up here, well, only 5% of the scores are going to fall in that region, and so we would call this the reject region. What that actually means is we're rejecting the null hypothesis, which says it didn't work, and the researcher likes rejection. The researcher is very happy because now this is a significant result. So let's look at the same thing, except let's look at a one-tailed low test. So let's erase everything that we just took our time to draw, and let's look at what this would look like in a one-tailed low test. So let's imagine now that the researcher is looking for a sample, a score that's in the low region if the medicine is effective. And the example that we might consider using is that example from before of trying to reduce eczema symptoms. The researcher predicts that eczema is lower with medicine. So the researcher wants a score in this lower tail. And the researcher set alpha to 0.05. So we have a one-tailed low test with alpha is 0.05. 0.05. The researcher wants only a 5% chance of making a mistake. So once again, we know certain things about distribution. We know that 84% of the scores are going to be, in this case, to the right of this standard deviation line. We know that 98% are going to be the right of this standard deviation line. So I'll draw a dotted line going all the way across here. 98% of the scores. What we're looking for is 95%. Where did the 95% come from? Well, we're looking at the odds that our score is in the tail. So 84% would be the same as saying alpha is 0.16, because that is obtained by taking 1 minus 0.84, or 100% minus 84%. In this case, that 98% would be the same as saying alpha equals 0.02. 2% of the scores will fall to the extreme of this score. What we're looking for is 95%, which is going to be somewhere around here, which is alpha equals 0.05. So we're looking for a score that's going to be somewhere in here, between the 84 and the 98. And we know that only 5% of the scores are going to fall in this tail. We know that 98% of the scores are going to fall in this region. And I said 98, and I hope you caught my mistake, because we're using alpha 0.05, so I should have said 95% of the scores are going to fall in this region. %. And in this region right here, 5%. And so in this case, if alpha is set to 0.05, and we know that 5% of the scores are going to be in this lower tail, and our sample gets a score in this lower tail, there's only a 5% chance that we just got that score just at random. We just pulled a sample and we got lucky. There's only a 5% chance of getting a score in this region. And so this is our reject region, where the researcher is happy. What are we rejecting? We're rejecting the null hypothesis, and we have a significant result. In the center here, if we get a score that falls in that region, we fail to reject HO. And the researcher might be sad because this is a non-significant result. So let's move on. This is what we've just described. What if alpha is set to 0.01? Let's get out the eraser and see if we can look at what this would mean. So there is our 5% region, So we just figured out where we would draw the line if alpha is set to 0.05, but now what if it's one-tailed low, but instead of alpha set to 0.05, we have alpha is 0.01. The researcher wants only a 1% chance of making a mistake. And we can see already that the 2% line is right here. So even if we drew the line way there, we'd still have 2%. So in a one-tailed low, we'd have to draw the line even lower. It would have to be someplace way here. Just this tiny little tail is where the cutoff point would be. This is where the axe is, so to speak. This is where we draw the line. And this is alpha equals 0.01. And we want 99% of the scores would be in this region. So in this case, if the researcher obtained a score that was anywhere above this one, anywhere in this whole distribution, which is where 99% of the scores are, 99%, the researcher would fail to reject HO and would be sad because it's not significant. But if the situation is just a little different and the score for the sample falls in this region right here, this teeny tiny region, well, there's only a 1% chance of getting a score in this region because alpha is set to 0.01, only a 1% chance. And if the score fell here, we would reject the null hypothesis. The researcher would be happy, and we would have a significant result. The researchers say the probability of getting such a score by chance is less than 1%. And without drawing the whole thing over again, if we just went and flipped this over, we would have the same thing except on the opposite end if it was a one-tailed high test. So that's how we do this in a one-tailed low test. But what do we do if we have a two-tailed test? So when we do these calculations, we're actually not going to use a table. Just like in the normal curve distribution, we're going to be using a calculator to determine alpha. And all that means is the z-score associated with the cutoff point. So in a two-tailed test, we look at this a little bit differently. We still set alpha the same. We still might set alpha to 0.05, meaning we want only a 5% chance of making a mistake, so there's no change there. This is the same as in a one-tailed test, but the difference is we have to divide this 5% into both tails. So we still have alpha 0.05, but now it needs to go between the two tails. And so half of the 0.05 is going to be here, 2.5% in this tail, and 2.5% in this tail. So we can see that if we drew it right at the 2 standard deviation line, we'd be getting 2% plus 2%. So we know we're going to have to draw our cutoff point a little bit further in toward the center and a teeny bit further in toward the center here, right wherever the 2.5% is. And in this case, we would consider it a statistically significant result if the sample score was found either in this region or in this region. And so a low score or a high score could both get a significant result. We still have, in this case, 95% of the scores are going to be in this center region. (95%) are found in that center region, and we're still going to call that center region our fail region, where the researcher is unhappy because he cannot reject the null hypothesis. The null hypothesis is dominant. It stands. This fail to reject HO. The researcher is sad because it is not significant. These tails are our reject regions. Reject HO, reject HO. Likewise, if alpha was set to 0.01, then we'd be sliding this over even further to wherever 0.5% in this tail and 0.5% in this tail, this researcher is really sure of their results. It's the same. And so here are the key concepts. The first is alpha, and remember that's the significance level set by the researcher for the probability of error that he or she is willing to accept. It's almost always, in fact it is always in our assignments, going to be 0.05 or 0.01, meaning that the researcher is willing to accept a 5% chance of error or a 1% chance of error. And when you'll find it in the problem itself, it will be stated. It will say alpha equals 0.05, or maybe the significance level is 0.05 or 0.01. If it's not stated, always assume it's 0.05. The p-value is the statement about significance that you'll write in the conclusion statement after you decide whether to reject the null hypothesis. So you're just going to be writing either p is less than 0.05 or p is less than 0.01 if you reject the null hypothesis. If you don't reject the null, you'll write NS for not significant. And p itself stands for the probability of getting a score this extreme from a sample chosen at random. One-tail test used when the researcher predicts a direction, like population 1 will have higher or lower scores than population 2. In this case, all of alpha, or all of the critical region, will be in that one tail. And two-tail tests are used when the researcher doesn't predict a direction, such as population 1 will have different scores from population 2. And in that case, alpha is divided between the tails. And the cutoff point is the standardized score, or the z-score in this case, that we'll be using, that's needed to reject the null hypothesis. It's like where we draw the line for where to mark the shaded region on the tail of the z-distribution. The shaded region is also called the critical area or critical region. The z-score for where to draw the line is called the critical value.